Okay, so let's get into it. We're diving into graphene today.
Right.
That material you hear about all the time, the miracle material.
Right.
Right? Super strong, great conductor.
Absolutely. But there's always been that one big drawback.
The stiffness.
Yeah.
Yeah, it's incredibly rigid,
Mm-hmm.
which is great for some things, but, well, not so much for others.
Exactly. Think about like flexible electronics
Yeah.
or wearables. Stiffness is kind of the enemy there.
Definitely. But there's some new research out that might just flip that on its head. A way to make graphene stretchable.
That's the headline finding, yeah. It's really fascinating stuff coming out of the University of Vienna.
Published in Physical Review Letters, I saw.
They basically uncovered this hidden property, something that wasn't really seen clearly before because of, well, how people were looking at it.
Interesting. So, okay, that's our mission for this deep dive then. We need to unpack how they did this.
Yeah, how do you make something famously stiff suddenly? Bendy.
And what's this accordion effect they're talking about? That sounds intriguing.
It's a great analogy, actually. Really helps visualize the mechanism.
And then, of course, what does it all mean, for actual applications down the line?
Right. It's a deep dive into some really meticulous science, revealing something quite unexpected about a material we thought we knew pretty well.
Okay, so graphene, isolated back in 2004, right? The classic 2D material.
Yeah, the original. Yeah, just a single layer of carbon atoms, one atom thick.
And that structure, that perfect honeycomb lattice, that's what makes it so strong, but also so stiff.
Precisely. Those carbon bonds are incredibly tight in that flat sheet.
So scientists had this idea, logically, to maybe introduce defects, right? Like knock out a few atoms, create little holes, vacancies.
The thinking was maybe that would disrupt the lattice enough to soften it up a little.
Makes sense. But the results from earlier experiments trying that were, well, they were all over the place, weren't they?
Totally confusing. Some studies reported a bit less stiffness, yeah, but others found it actually seemed to get stiffer with defects. It just didn't add up.
So what did the Vienna team do differently?
This is the crucial part. They realized the inconsistency might not be inherent to the graphene itself, but maybe it was the environment they were testing it in.
The environment. How so?
Well, they used really sophisticated tools, scanning transmission, electron microscope, atomic force microscope. But the key innovation was doing it all inside one continuous, ultra-clean system, completely airless.
Ah, okay. An ultra-high vacuum system.
Exactly. So they could prepare the graphene, introduce the defects, and then measure its properties without ever exposing it to normal air.
Why is avoiding the air so important? I mean, graphene's pretty tough stuff, isn't it?
It is tough, but remember, it's only one atom thick, and air isn't just empty space. It's full of tiny particles, contaminants, moisture.
Right. Dust, aerosols, whatever else is floating around.
Precisely. And the Vienna group, led by Johnny Kotakowski, figured that maybe these tiny stray particles landing on the graphene surface were messing up the measurements in previous studies.
Like adding little unwanted reinforcements or something?
Or just interfering with how the material could deform. Well, Judy, the first author on the paper, pointed out this was the first time this kind of mechanical testing on defective graphene was done completely isolated from ambient air.
So by keeping it ultra clean.
By keeping it ultra clean, they got rid of that environmental noise, as you could call it, and then they saw the true effect of the vacancies.
And that's where the accordion comes in.
That's exactly where it comes in. They found that when you create a specific defect, removing two adjacent carbon atoms, it doesn't just leave a hole, it causes the normally flat graphene sheet to sort of pucker up, to bulge slightly around that missing pair.
Oh, interesting. So the defect creates a little bump.
Yeah, a tiny ripple. And if you introduce several of these specific defects across the sheet,
You get multiple ripples, like corrugations.
exactly, the whole sheet develops this subtle, wavy texture. And that's what Whale Judy compared to an accordion.
Okay, I can picture that. An accordion has folds, right? And when you pull it, you're not really stretching the fabric of the folds.
You're just straightening them out.
Right. You're flattening the creases. And that takes much less force than trying to, stretch a solid, flat piece of cardboard to the same length.
That's the perfect analogy. When they applied a stretching force to this rippled graphene in their clean setup, the first thing that happens is those ripples start to flatten out.
Ah, so the initial stretch is just the accordion unfolding.
Precisely. And unfolding those ripples requires significantly less force than trying to directly pull apart the carbon bonds in a perfectly flat, pristine sheet.
And that reduction in the force needed,
Hmm.
That's what they measure as reduced stiffness,
Yeah.
making it seem softer, more stretchable.
Exactly. The material becomes effectively more pliable because it has this built-in mechanism, the ripples, to accommodate the initial strain.
Wow, so the vacancies under clean conditions actively create the structure, the ripples, that enables the stretchiness.
Correct. And they had theoretical physicists on the team run simulations too, which confirmed it. The vacancies caused the ripples, and the ripples explain the stretchability they measured.
Okay, but then what about those older studies? The ones where defective graphene sometimes seems stiffer. How does this explain that?
That's the other key finding from the clean environment. They explicitly tested what happens when you let those airborne particles land on the rippled graphene.
Yeah.
And those particles basically gum up the works, they land on the surface, and they suppress the formation and the movement of those accordion ripples.
So the particles prevent the accordion from unfolding easily.
They do. They kind of pin the ripples down. And not only does that stop the stretchability effect, but the measurements taken with the particles present actually made the material appear stiffer again.
Just like in those old, confusing studies.
Exactly. It perfectly explains the discrepancy. The contamination wasn't just noise. It was actively changing the measured mechanical properties, hiding the true accordion effect.
That's incredible. It really highlights how critical the experimental conditions are, especially at the nanoscale. A few stray particles make all the difference.
It's a stark demonstration, as Whale Judy put it. You have to control the environment just as carefully as the material itself when you're dealing with these single-layer systems.
So it wasn't some fundamental paradox in graphene, just interference?
Interference that masked a really interesting property, and it suggests, potentially, a new way to control graphene's properties.
How so?
Well, if the presence or absence of these surface particles influences the ripple behavior and thus the stiffness, maybe we can actively tune the stiffness, not just by creating defects, but perhaps by carefully controlling the surface environment or adding specific molecules intentionally.
Which brings us back to the potential applications. If we can reliably make graphene stretchable, and maybe even tune how stretchable.
Then those ideas about flexible displays, truly wearable sensors that conform to your body, maybe even flexible biomedical implants,
Yeah.
they become much more feasible.
Yeah, the possibilities really open up if you can engineer that stretchiness reliably.
It moves graphene beyond just being strong and conductive, adding this crucial element of mechanical flexibility.
Okay, so let's sort of wrap this up for you, the listener. What we've seen here is pretty remarkable.
Yeah, it's a great story of scientific detective work, really.
By creating very specific, tiny defects, just removing a couple of atoms, and by doing it in an incredibly clean, air-free environment.
That combination was key.
Scientists managed to reveal a hidden behavior in graphene. These defects create ripples, like an accordion's folds.
And those ripples allow the graphene sheet to stretch easily by unfolding, making it much softer and more pliable than we thought possible.
And this discovery also solved that old puzzle of why previous studies on defective graphene gave such contradictory results.
Right. It turns out tiny bits of contamination from the air were hiding the true effect all along.
It's a powerful reminder, isn't it, how much the environment matters, especially when you're working at the scale of single atoms.
Absolutely. Sometimes the smallest, seemingly insignificant factor can completely change how a material behaves, masking potentially revolutionary properties.
Which leaves us with a final thought to consider. If simply controlling whether a few stray particles are present or absent can fundamentally alter a material like graphene, turning it from stiff to stretchable, what else might be hiding in plain sight?
What other amazing properties might be lurking within materials we think we understand fully, just waiting for us to create the right, perfectly controlled conditions to reveal them?
It suggests that the future of material science might lie just as much in controlling the environment around the material as in engineering the material itself. There could be a whole world of hidden behaviors waiting to be discovered.